Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss Coulomb or transverse gauge. Let's begin. The two coupled Maxwell's equations in terms of electromagnetic vector and scalar potentials are given by two set of equations, one in terms of vector potential, another in terms of scalar potential. These two equations we have already derived in the chapter named as Maxwell's equations in terms of scalar and vector potentials. Here we use Coulomb gauge condition in that two coupled Maxwell's equations. Using Coulomb gauge condition. What is Coulomb gauge condition? Grad dot A is equal to 0. That is the Coulomb gauge condition. Then equation 1 and equation 2 change to equation 1 change to equation 1 under 2 changed to the new form grad square A vector minus mu epsilon del square A del t square minus grad dot A as 0, that grad is multiplied to this one, therefore it will be mu epsilon grad dot del phi by del t is equal to minus mu j vector, or that term to this side grad square A vector minus mu epsilon del square A vector del t square is equal to mu epsilon grad del phi by del t minus mu j vector. That is equation number 3. And in equation number 2, grad dot A as a 0, that is the Coulomb gauge condition, then that equation 2 change to grad square phi minus mu epsilon del square phi del t square plus grad dot A as 0, this term mu epsilon del square phi by del t square, mu epsilon del square phi by del t square is equal to minus rho by epsilon plus minus cancel out, we obtain grad square phi is equal to minus rho by epsilon. That is equation number 4. Look that equation number 4 carefully, that the Poisson's equation, this equation this equation represents the Poisson's equations. Poisson's equation. So its solution can be represent phi as a function of xt, position and time, is equal to phi is a function of xt is equal to 1 by 4 pi epsilon integration over rho x alpha dash t divided by r dv dash. Phi as a function of x alpha t. What are these terms indicating? If we consider a source S, the coordinate x alpha dash t, then the field f having the coordinate x alpha and t, and distance between the source and field r. Source where there will be magnetic fields or electric field, and field we can measure the potential. Where x alpha t, that is the coordinates of the field point, coordinates of field point f, x alpha dash t, that is the coordinate of source point S, r the distance between field point and source point, and dv dash any arbitrary volume of that of source element, arbitrary volume element at that source S. That solution in the short form we write phi is equal to 1 by 4 pi epsilon integration over rho by r dv dash. This is equation number 5. This is the solution of that equation number 4. Again, to solve that equation number 3, first we have to calculate the current density term J, and then putting that solution phi, we can easily get the solution for A vector. Okay. Now, current density J vector is equal to its longitudinal component and its transverse component. Equation number 6, where JL, that is the longitudinal component of current density, and JT, the transverse component of current density. And it is a condition, for longitudinal component of current density and transverse component of that of current density is that the curl of that longitudinal component is equal to 0 and the divergence of that transverse current density component is equal to 0. Now, we can use vector calculus, vector identity. Using vector identity, that grad cross j is equal to grad dot j minus grad square j. Or grad square j is equal to grad dot j minus this term grad cross j. Grad square in place of j, that is longitudinal component plus transverse component, grad dot j minus grad cross j, separating it in two terms, grad square all terms, grad dot j minus grad cross j. Now, comparing the two sides of that equation, comparing both sides of this equation, grad square j longitudinal component is equal to grad of grad dot j. Equation number 7. And transverse component grad square, transverse component of that current density minus grad cross j. Again, clearly look these two equations named as equation number 7 and equation number 8. it is seen that it's the equation just like that of Poisson's equations. So, the solutions of equation number 7 and 8, then the solutions of equation 7 and 8 are no derivation required, only you have to remember that solution. The solution for longitudinal component of current density J L is equal to minus 1 by 4 pi grad integration over grad dot J divided by R dV dash is equation number 9, and transverse component, that is plus 1 by 4 pi grad cross grad of integration over J by R dV dash, equation number 10. Now, we use these solutions to solve equation number 3 in order to obtain the value of vector potential A. Now, from equation number 3, now equation 3 will be grad square A vector mu epsilon del square A vector by del t square mu epsilon grad del phi by del t minus mu in place of J, that is longitudinal component and transverse component, is equation number 11. To solve that equation number 11, first we have to solve that term. Here mu epsilon grad dot del phi by del t is equal to mu epsilon grad in place of phi, that is del by del t. Solution for phi 1 by 4 pi epsilon integration over rho by r dV dash, 1 by 4 pi epsilon integration over rho by r dV dash is equal to, here epsilon cancelled out, that is the constant term to that of outside. Therefore, mu divided by 4 pi grad integration over del rho by del t divided by r dV dash. Del rho by del t can be calculated by using equation of continuity. Using equation of continuity, del rho by del t plus grad dot j is equal to 0. From that equation, del rho by del t is equal to minus of grad dot j, mu by 4 pi grad integration over minus grad dot j divided by r dv dash. Rearranging the terms as mu minus 1 by 4 phi grad integration over grad dot j divided by r dv dash. Why we write like this? As we previously derived, that is same to that of j l. Instead of this, we can write mu j l, equation number 12. Therefore, the value of that mu epsilon grad dot del phi by del t, which one is equal to mu j l vector, now put it in that of equation number 11. To solve that equation number 11, we have to put that value. Therefore putting the value from equation 12 in equation 11, we get in equation 11 grad square A vector minus mu epsilon del square A del t square is equal to, in place of that term we use mu j l vector minus mu j l vector minus mu j t vector, mu l vector mu j l vector cancelled out. Grad square minus mu epsilon del square by del t square over that of A vector is equal to minus mu j t vector. This one is D'Alembertian operator, square box square, or generally square box. These four sides of that of square represent 4 coordinates, 3 position coordinate, 1 time coordinate. Basically that type of operator is used in case of space time phenomenon. A vector minus mu j t vector. See the solution. The equation number 12, where grad square is equal to, square box square is equal to grad square minus mu epsilon del square by del t square, which is D'Alembertian operator. Look that expression. Here there will be the no component of that longitudinal current density term, only transverse component term exists. For that reason, that type of Coulomb gauge we called transverse gauge. Since no term having longitudinal current density but only transverse current density term, in that expression, therefore that type of gauge we call it as transverse gauge. So, that Coulomb gauge also called as transverse gauge. Looking that scenario, Coulomb gauge condition, this grad dot A is equal to 0 is often used to when there will be no source present, no source are present, means phi is equal to 0. When phi is equal to 0, so E vector is equal to minus grad phi del A vector by del t, as phi is equal to 0, therefore E is equal to minus del A by del t, and B vector is equal to grad plus A. So, by using Coulomb gauge condition, when there will be no source present, that scalar potential field will be 0. So, electric field and magnetic field can easily be calculated by using A vector, vector potential field. So, here with the help of this video lecture, we understand the concept of Coulomb or transverse gauge by using two coupled Maxwell's equations in terms of scalar and vector potentials. Coulomb gauge condition, grad dot A vector is equal to 0, then these equations reduced, that form equation number 3 and equation number 4. That equation number 4 is the Poisson's equation and its solution. Again, the solution of equation number 3 can be obtained by using current density. Current density have two components, longitudinal as well as transverse. Longitudinal and transverse components are related with each other by that equation. Using that vector identity, we obtain that one, and the solution of these two equations, and finally these solutions are put in that of expression 11. That term can be simplified as this, and finally we have the solution square bracket square A vector is equal to minus mu z t vector. That square bracket is called the Albertian operator, which indicating that only existence of transverse component, therefore it is called transverse gauge, transverse gauge. When there will be no source field present, then electric field and magnetic field in terms of scalar potentials. So, with this useful and informative notes, let me wind up the session. Thank you.